All right, so thank you all for being here. Today I'm going to be talking about a recent paper that just recently got accepted for a CLR. So you're going to go to the conference, let me know. I'd love to hang out and talk more about the research over there. You can learn more about the paper on the archive link. The camera ready should be up soon. And there's also a QR code over there if you want to learn about it. So the agenda for today is that first I'm going to be talking about the Kolmogorov approximation theorem or the superposition theorem. It does go by many names. I'm going to talk about the theory of it, some computational approaches it has inspired throughout the years. And then I'm going to talk a little bit about physics-informed neural networks, and finally delve into the experiments that we did in this paper. So first off, I want to talk about a little bit about the star of the show right now, which is the Kolmogorov superposition theorem. So this theorem was originally proposed and proved in 1957 to answer one of Hilbert's problems from earlier in that century. So this theorem not only answered this Hilbert's 13th problem, but it also was a much more broad theorem that had other implications and is much stronger than what it was just trying to prove with the Hilbert's problem. So the theorem, the original version, goes as follows. Let f be a continuous function from the d-dimensional cube to the real numbers. Then it can be represented exactly using this formula over here, which I'll explain in a bit, where the functions g, which, let me see if I can show, there we go, I can show my cursor. These g functions over here are known as the outer functions, and these phi functions over here are known as inner functions. So one thing that is important to say is that both these functions, g's and phi's, they're all continuous univariate functions, okay? And the theorem for this says that furthermore, the inner functions are independent of the function f. So that means if you change to a different function that you want to represent in the same input dimension, all you have to do is change these outer functions over here. So what is the usefulness of this theorem? Why do we care about it? One very interesting thing is that this gives us a way to exactly represent an arbitrarily complex function, as long as it's continuous, in n dimensions using only univariate functions. That is the key insight over here. So this function, f, is a function of many inputs. But each of these functions that you see over here, both the outer and the inner functions, are all univariate functions. So this tells you that all the information that is embedded in this multidimensional space can be represented exactly via continuous functions of only one dimension. So in a way, some people talk to this theorem about this theorem as saying that the only true multivariate operation you can have is composition and summations, which is what you have over here. All the other things that are happening on the univariate functions, which in general are much easier to approximate from numerical methods, right? And another very important thing of this theorem is that it gives you this representation using a finite and fixed number of univariate functions. You know, a lot of theorems give you like an approximation or like in the limit as it goes to infinity, or says there exists an integer n such that we can get this representation. This formula gives you an explicit number of like how many functions you need, right? So you can see here that these indices go from p equals 1 up to d, where d is the input dimension. I'm going to be using this notation throughout the talk. And over here, the q goes from 0 up to 2d. So this gives you like a constant number of functions given the input dimension that you need to use. So that is very attractive for a lot of applications in math, both computationally and theoretically, right? And indeed, several years later, so there's already 3 decades later, there was this researcher called Hatch-Nielsen that really tried to pioneer the use of this theorem for neural network applications. So this is something that's been going on already for about 40 years. And you can see over here, I think this is really interesting, although Kolmogorov's theorem was both powerful and shocking, many mathematicians do not believe it can be true when they first see it. It has not been found to be of much utility in terms of its use in proving other important theorems. In mathematical terms, no one has found a significant use for it. And then it goes on, the point of this paper is that this is not the case in neurocomputing, which is how they talked about neural networks back in the 80s. So this was actually a very hot take for the time. And for example, about a year and a half, 2 years later, there's this other paper from Thomas Poggio over MIT talking about Kolmogorov's theorem is irrelevant, right? And they did have good reasons to talk about this. And particular is this one. A number of results by Wittgenstein, and these are from also really old theorems, show that the inner functions, so those functions that are required for that approximation, are not smooth. They are continuous, but they can be seen kind of like hashing functions. And this wild behavior makes it completely inapplicable for anything that you would do using computers, right? You need to do floating point arithmetics. If you have something that has an infinite number of non-differentiability, you're going to get into a lot of problems. And this is indeed the case in a lot of the constructive proofs for this theorem. You can see that the construction of these inner functions do have this very chaotic kind of Cantor-like behavior. If you've seen the Cantor function or the devil's staircase, you've seen something like that. This function over here, for example, it is continuous. It is even monotonic increasing, but you can see as you keep zooming in and in, you get an infinite set of non-differentiability. And this is bad news for anything that has to be done in a computer or anything that has to be approximated, right? So that's not a very motivating start. Having said that, that didn't stop people from trying. And in particular, just a few months ago, this paper, Kolmogorov-Arnold networks, came out trying to exploit some of the properties of that theorem for neural network design. So this paper got a lot of attention on social media and within the research community. Raise your hand if you've seen at least something about it online. Whether or not you read the paper, at least you've heard of the paper, a lot of people, right? So what's up with this, right? Haven't people talked that there's no point in using these types of things? Well, yes and no. So let's look again at this theorem a little bit more in focus, right? So as I said, the main criticism is that you can prove in many ways that in many cases that these inner functions over here are very wild. They're non-smooth and not very easy to be approximated and computed efficiently, right? But there's a few caveats to that. First off, that hashing behavior that you see from those constructive proofs largely comes from the fact that we require these inner functions to work for all continuous functions f from this d-dimensional cube to the real numbers, right? So if instead we want this approximation to work only for a single function or for a subset of continuous functions, maybe this wild behavior is not necessary, right? This wild behavior, you can prove that it is necessary when you want this universal property for the inner functions. If we allow the inner functions to change depending on the function f, maybe there's some hope that they will not be as wild. Another thing is that this formula gives us an exact representation, right? That's really powerful and really interesting, especially for proving theorems. But in reality, any machine learning work that we're going to do, we're never going to have truly an exact representation. We're always going to be looking at approximations. Also, because of floating point arithmetic, most of the time, you can't even ever hope to have an exact representation, right? And so that also begs the question, if we only care about approximating a function instead of exactly representing it, up to some epsilon, is it true that these functions still have to be non-differentiable on a very large set? Maybe not. Maybe we can approximate it using differentiable continuous functions. And another point that also that Kahn paper emphasized is that this formula, this representation, kind of works on two layers, two levels of compositions. You have your inner functions over here, right? That they do something to your input x, and then you kind of sum them over, and you still have 2D things that you end up going to sum, but then you do another composition of these g functions. What if we decide to go further? That's something that in practice we've seen a lot of success in deep learning, is just increasing this compositional structure of formulas does give you a lot more expressivity, and it enables you to approximate a much richer class of functions. So all these things are a little bit hand wavy, but they are true. And I would say that at the very least, motivates more research into looking into whether it's possible or not to use these types of theorems to design or understand neural network architectures. I will say something. As I said, this theorem is from 1957, so a long time ago. And since then, mathematicians have been working on this for over half a century. And from then, a whole zoo of different versions of this theorem came around, all with different assumptions, slightly different structures to their formulas. And that Kahn paper, Kolmogorov-Arnold networks, used the original one as inspiration. And this that I have over here is just like a small subset that I got, like 4 of them, but in reality, there's like over a dozen. And then this backs to the question, like, where do we start? Is the original one really the best one to go on and try to design neural network architectures? There are other options. There are like attractive properties from other of these representations. And as you can see over here, the original formulation is actually the only one that has a number of functions that scales as O of D squared. All the other ones, at least the ones that I'm showing here, scale linearly with the input dimension D. And there's a bunch of other assumptions and like differences in the peculiarities of the theorem. So which one to pick? And my goal for the next little bit of this talk is to argue that and convince you that this last one, the Laczkovich version, is maybe one of the best suited ones. So let's talk a little bit about that version of the theorem. There we go. So this version, I'm going to call the Laczkovich KST. And by the way, I will refer to all of these theorems here collectively as superposition theorems going forward. So the Laczkovich version of it says the following. So let D be any natural number. So again, D is the input dimension. And M be any integer that is at least that big. So you can see it grows linearly with input dimension D. So this is any integer. So the theorem says that there exists constants lambda ij, where I goes from 1 to m and j goes from 1 to d, along with continuous functions phi I, and as again, I goes from 1 to n, such that for any continuous function f from Rd to R, now notice, now we're talking about Rd, no longer we're talking about just the unit cube. There exists a continuous function, a single one, that is also univariate, such that we get this formula over here. So, okay, so what are the similarities and differences from the other version that we saw? So similarities, you also have these inner functions over here, and outer function compositional structure. In this case, however, instead of having O of D squared inner functions, you only have O of D, and you only have a single outer function, okay? And another benefit, as I said, is that the input dimension, the input space, the domain is no longer restricted to be a unit cube. It actually is valid across all of Rd. Okay, so to summarize, so as again, the domain is now valid across all of Rd as opposed to just the unit cube. It has this flexible width representation. So over here, the original theorem said explicitly about setting 2D over here. In this case, it's valid as for any integer as long as m is this big. The number of unknown functions in this formula scales as O of D as opposed to O of D squared, and I'll talk about it later. There is some interesting interpretations of this formula using some modern deep learning lenses. So let's use a little bit of vector notation to make things a little bit simpler going forward. So this same formula can be written in this manner over here in red if we use the following notation. First, we set this capital lambda to be a matrix where the ij entry is equal to lambda ij. We set this capital phi here to be a function that given an input x, the ij entry of this matrix is equal to phi I of xj. I'm going to call this the inner basis expansion. Okay, so it kind of like expands. So inner function expansion, sorry. It's going to like expand and give you all the possible combinations of phi I xj. And this S function is just going to be something that's going to compute the row sum of a matrix, or the sum of the elements if the argument is a vector, okay? So using this notation, this same formula over here can be written in this form. It's a little more convoluted, but it is simple to write, and I'm going to be talking more about this way of writing it in a little bit. So what are we going to do with this formula? What is our plan? So our plan is to try to use it to create some sort of like way to approximate other functions that we care about, right? The way that we're going to do this is we're going to have to learn what these inner functions and outer function is, and also learn what these constants lambda are. So the way that we're going to do this is we're going to learn these unknown functions as a linear combination over a set of basis functions. So this is very standard. We're just going to set some basis functions b1 up to bn, and we're going to learn it as a linear combination via these coefficients beta over here. Okay? And our goal is that we're going to learn these constants lambda ij along with the constants beta via gradient descent from some data or some other training method that we care about. And another thing that I'm going to be getting to in a little bit is we're going to also try to make this compositional structure like deeper. We're trying to go further with this representation so we get like more layers, so to speak. And just to emphasize, like, again, when we say layers, I'm meaning that like there's like one compositional structure. There's one round of functions over here. They get like summed up, and then we compose it with another thing. So every composition, when I talk about layers, I'm talking about more compositions. Okay. All right. So once again, talking a little bit about linear algebra and vector notation, if we approximate the inner functions in this form, this can be equivalently expressed as beta times b of x, where again here b is basically the basis expansion. Once again, it's going to be a matrix. Bx is going to be a matrix where the kj entries is bk of xj. And this beta is going to be another matrix that is n cross d, where the entries is beta ij. And so this same block over here, the S of capital lambda, this is the Hadamard or element-wise product with the inner function expenses, reduces to this. So now we have something where like the things that we want to learn are all just like real numbers. There's going to be the matrix lambda over here and the matrix beta over here. Those are going to be like, or learnable parameters that we're going to try to do. And I'm going to talk a little more about like why this part over here in blue is what we care. If we want to represent this, I guess in a visual diagram, what this is doing is that the ith entry of this thing, right? So this thing in blue is a vector in Rd, and the ith entry is going to be equal to lambda I dot product with phi I of x, where this phi I is being applied element-wise. And lambda I is kind of is the row of that big matrix capital lambda. So if we do it in this way, this actually looks very similar to a lot of things that we see in neural network, where you kind of, if you just look at one of these paths over here, we have our input x. It is passed through like a non-linear function element-wise. So this kind of fills the role of an activation function. And then we map that using a dot product to a different dimension, in this case, R, so R1. So this can be seen, each one of these paths can be seen as like a tiny multi-layer perceptron, like a dense layer of a neural network, where we have a tunable activation phi I, and the output dimension is 1. And this is actually a very interesting idea, because if we do something like this, there's two mathematically equivalent ways of viewing this operation. One is going through the Laczkovich version of the Kolmogorov Superposition Theorem, which we talked about, and that's how we derived this specific like block. And if you're familiar with the transformer neural network, the architecture, something that it does is that instead of having, for example, one large attention block, it has several small attention units that are run in parallel and then concatenated at the end. And this is exactly what's happening here, but instead of having a small attention block, we kind of have these like small multi-layer perception layer blocks, where each one of these heads computes the forward pass of a simple layer from a multi-layer perceptron. So this gives like an interesting interpretation because now we're seeing this through different lenses, right? We're seeing each head is kind of like independently doing something, and then we're concatenating everything together. And this does lead to a lot of like interesting gains, for example, in the other like deep learning literature. Okay, so this gives us our basic building block of the architecture that I'm building upon. So this gives us what I called an ActLayer. Why did I call it an ActLayer? Well, it's because we have these tunable activations, and so I thought it would sound cool with ActLayer. So, okay, are we done here? How does this relate to the theorem? Where do we go from there? So if you see, in this case, our input to this ActLayer block is x, which is a vector in Rd. And as output, we have scalars in the reals, but we have m of them. So the output is practically in Rm, right? So this kind of gives us a building block that goes from Rd to Rm. And nothing's stopping us from composing more of them together, right? And this is something that we see over and over again in a lot of deep learning literature, is that you do gain a lot of expressive power by composing building blocks together. So the end result that we get is what I call the ActNet, that you have an input x, and we compose a lot of these act layers. And in addition to that, I also have a linear projection at the very start and a linear projection at the very end to help fix the latent dimension or the output dimension. And also in some experiments, I found that this helped a lot with performance, and it doesn't really hurt any of the expressivity power of our network. So one big advantage of this, which is based on the Laczkovich version of the KST, is that we actually get universality. And what do I mean by universality? I mean in the following sense. So if we have a given set omega in Rd, a neural network architecture is called a universal approximator on that set if for every continuous function and every epsilon greater than 0, there exists some choice of hyperparameters and trainable parameters, theta, such that the function f theta computed by this neural network architecture satisfies this. It says that your true function minus the approximation over here is at most epsilon away at all points. So that's what we mean when we say universal approximation. For an architecture, you just say that it can approximate a continuous function arbitrarily well if we pick the right combination of hyperparameters and trainable parameters. And indeed, you can look at the proof in the paper, but if we compose two of these act layers together from the Laczkovich version of the KST, we do get this universal approximation property, assuming that we pick a right basis functions. This is not necessarily a surprising theorem, I would say, but it's a good sanity check. For any neural network that comes out, it is something that is, this is like the not exceptional, but is the very least that a neural network should have. And so it's like good that we do have this theoretical guarantee. And another thing that I haven't really talked about very much is the choice of these basis functions, right? And can people see this, or should I close the blinds a little bit? It's good? Okay. Oh, what? You can see? Okay, beautiful. Sounds good. So as I said, the inner functions that we have over here are approximated this way, right? A linear combination of basis functions. And the specific type of basis functions that I use for this architecture is as follows. So these BJs are kind of normalized versions of a Fourier basis. And what do I mean by normalized versions? We have this formula that is going to be like sine of omega j times, and say these are all univariate functions. So let's say the input is t. So it's going to be sine of omega times t plus some phase. So you have your frequency parameter omega and your phase parameter p. And then I subtract this mu and divide by this omega. Okay? What are the mu and omega? This is actually something that is interesting because in a lot of deep learning literature, you work under the assumption that the inputs to a layer are going to be normally distributed with mean 0 and variance 1. So in building these basis functions, what I worked on was, okay, let's assume that this is indeed true, and we have that the inputs to this layer are normally distributed with mean 0 and variance 1 and following a Gaussian, right? In this case, mu is, so let's say that x is a standard normal, and so mu is the expected value of this transform random variable sine of omega x plus p, and sigma squared is going to be the variance of this new random variable. Okay, so what we're doing over here is we're effectively removing the mean and then dividing by the standard deviation, and that means that if the input to this basis function is a standard Gaussian, then the output will at least have mean 0 and standard deviation 1. Why is that important? Well, it's important because as you compose more and more layers, if, say, like the standard deviation of this thing is 5 or 10, when you compose more of it, these activations are going to start blowing up. And if they're less than that, if they're less than 1, if they're like 1/2, with each layer, the activations are likely to decrease and vanish to 0. So we do want to be on that sweet spot that is going to maintain the activation stable throughout the network. And this is the case. There's not a theorem that I prove in the paper that shows that at initialization, if the input is distributed as a standard normal, then each of the output of the ActLayer has mean 0 and variance 1. So it has mean 0 and variance 1. Also, in the limit, as the number of basis functions goes to infinity, or the infinite dimension goes to infinity, we get that not only do they have mean 0 and variance 1, but they're also normally distributed. We get that from the central limit theorem. So this kind of gives us a bit of a sanity check that as we compose more and more blocks, we get stable activations and a stable phenomena throughout the network. Okay? And another quick thing, so just to summarize and compare to some of the other architecture out there. So over here we have the different hyperparameters, parameter count, and the number of flops for a given architecture. So you can see over here I compare an ActNet, Kolmogorov-Arnold network, a KAN, and a multi-layer perceptron, MLP. So all of them have in common that they have a depth and some notion of hidden dimension. Okay, in this case, the hidden dimension for the ActNet is the m that we're talking about, the number of inner functions of those blocks. In addition, for the ActNet, you have another hyperparameter, which is the basis size. How many basis functions are you including in your set? So the MLP only has the depth and width, and a KAN, in addition to depth and width, also has, in order to approximate those functions that we were talking about from the original version, instead of using a linear combination of basis functions, they actually use B-splines. So to use a B-spline, you have to pick like a spline order and a grid size to have your, like, I think they call collocation points. So in that case, you have these other added hyperparameters G and K. Okay, and K is usually 3, but G can be upwards of like 100, 200, and more. So as you can see over here, MLP is definitely the one with the least parameter count. ActNet has something very similar because it's LM times M plus N. Okay, and I'll talk about what is a wise choice for N. Whereas KANs over here have LM squared times G plus K. The K over here is pretty small and usually constant equals to 3, but this G, depending on the problem, can grow, and they do use like much finer grids up to like 100, 200, a few hundred sometimes. And in addition, the number of flops over here, as you can see, these KST approaches are indeed a little more expensive. But first, let me talk about the effect of this basis function n. So the basis function, the number of basis functions, right? So in experiments, I actually found, I didn't expect this, but you don't actually need a lot of basis functions to get good behavior. In fact, if you see over here, this is for one of the problems that I'm going to talk about in a little bit. We see that what happens, so these I run through like a lot of I run a hyperparameter sweep across different seeds, and I take the best hyperparameter based on the median. So this was a pretty thorough comparison. And you can see what happens over here. On the x-axis, we have the parameter count, and each of these graphs shows a different choice of basis functions. Okay, so you can see there isn't actually that much difference, right? as you increase the number of basis functions, you don't get much added performance, but if you see over here the computational complexity, it increases linearly with n. So with each graph that we go to the right over here, we kind of double, roughly, the computational complexity, but we don't really see many gains, even at a fixed parameter count. So that tells you that you can actually choose a very small number of basis functions for a lot of problems and get along with it. So for like most of the problems that I use, I actually set the default later on to n equals 4 basis functions only in each layer. And now, how can we get away with using only 4 basis functions? And it is exactly because of that compositional structure. We don't need each inner function to be extremely accurate or extremely performative because we can compose several of these blocks together. So if you compare it to an MLP, you can see that it's not that much different, assuming that n is small. And I will also say this also, we also have to take into account that some of these architectures to approximate a function well maybe need a smaller depth or a smaller hidden dimension. So it's not a direct apples to apples comparisons, but it gives an idea. Whereas cons, for example, over here, you have this k times g plus k factor, and in this does make a big difference in experiments. So for comparison, in a lot of the experiments that I ran, if the MLP is the baseline, con, depending on the problem, will run like 10 to 20 times slower. And ActNet does run a little bit slower, but on a factor of like 2 to 3, sometimes 2 to 4 times slower. So it is still slower for the same parameter count, but it improves a lot from cons. Okay, now let me take a little bit of a quick detour and talk a little bit about physics-informed neural networks, and I'll connect everything together soon. So I'm going to talk about a brief introduction. This is taken from a workshop paper that I did with some colleagues from my group. One of them, the very handsome Sham over there. And so what is a physics-informed neural network? So it is a way to approximate partial differential equations numerically, right? So let's assume that we have a partial differential equation that we want to learn the solution to via a neural network, right? So in this case, we maybe have some operator over here, this n, acting on the domain that we care about, omega. So we want this operator acting on the solution u, and this u is going to be computed via neural network, to satisfy some function f. And maybe at the boundary, we want to satisfy a specific value. So this is assuming Dirichlet boundaries for the PDE. It doesn't have to be the case. You can do periodic and other things. But let's assume periodic. Let's assume Dirichlet for now, for simplicity. So the idea behind physics-informed neural networks is that we're gonna use automatic differentiation to compute the derivatives of this function u computed by the neural network, and then we train it in order to minimize how well, to minimize how off the PDE residuals are. Does it sound complicated? Yeah, probably a little bit. So why don't we look at an image, which is easier to parse? So in this case, we have our deep neural network. You have our inputs, maybe like it's time t and a position x. This x doesn't have to be one-dimensional. It can be like 2, 3-dimensional. And we compute the forward pass of this neural network to get quantities of interest, maybe like v and sigma over here. And then from these quantities over here, using automatic differentiation that's found in packages like JAX, PyTorch, Julia, and so forth, you can actually compute what are, for example, the partial derivative of like sigma with respect to t, or the third partial derivative of x mixed with like x and t over here. So you can do all this very easily using automatic differentiation. And from then, we can see how well each of these quantities fit the PDE that we care about. That's going to give you like a residual loss, the physical residual loss, and we can also look at how well it fits the boundary condition, and then we can combine all of this together to get the final loss for your system, and then you can train the neural network this way so that eventually you hope that it satisfies your PDE. Okay, so this kind of falls in like a lot of things under the umbrella of a lot of things that people do in scientific machine learning, where sometimes you have a lot of data, and you don't know anything about your system. So that's the case, for example, in your like large language models and video generation, stuff like that. And sometimes, most of the time, actually, in scientific machine learning, you're not over here in this big data regime. You're in the space where you have a little bit of data, sometimes no data, but you do know a lot about the physical systems. And this is more of a heuristic, and there's several ways of enforcing this. But this physics-informed loss is just trying to help you when you're on the left side of this plot over here. You don't have a lot of data, maybe you don't have any data, but you do know maybe the governing laws about your physical system. You can describe it in a PDE, and then you can train a neural network to satisfy this PDE, to satisfy this physical constraints. Okay, so now why am I talking about this, right? What is the relationship to the other things? So the Kahn paper tried to apply to a range of different scientific computing tasks. And one of them, they did have like one small example trying to solve the Poisson equation with like a simple driving function. And they have these results. And then people actually became very interested in that, right? And then came another paper after that. And then came another paper, and then another paper, and then another paper, and then another paper, and then another paper. And then you get the idea, right? The cons were just like overloading the PINNs research, just like in the span of like 3 months after the Kahn paper was released. There were like, I don't know, like already like 10 papers. I haven't even kept track. There's way too more papers, and the paper came out like, I don't know, like 7-8 months ago. There's already more PINNs papers on cons than I really know about and can summarize. But there's just to get an idea. There's a lot of interest, and why is that, right? There's a few interesting things, in my opinion, why there's interest from the PINNs community on this Kolmogorov superposition theorem. One of them is that the target functions for these spins from physical systems can often be very complicated. Think about like, I don't know, the Navier-Stokes equation, the solution that has like a lot of like vortices and very complicated behavior, but they're still a relatively low dimension compared to a lot of the things that you see in deep learning, where like you have images where your pixel space is on the order of like 800 or like thousands, you know? And the representation properties of the KST have been a little bit better studied in this low dimensional domain than in this high dimensional one. Another thing that is very important is that a lot of these solutions to PINNs require solutions that have high frequency content. So if you run a Fourier transform, you're going to see there's going to be a lot of high frequency components in there that are really hard to approximate with plain MLPs. So if you use a plain MLP, they suffer from what are called spectral bias, where they learn the lower frequencies of a function really, really well, and then it takes a long time, and sometimes they just can't learn the high frequency components of the true solution that you care about. And another thing that is interesting is that when you train with PINNs, if you do it with random sampling, so you sample the collocation points randomly at each time at as a fresh batch, this kind of gives you, in a way, like, you don't need any like actual experimental data, but it gives you like infinite data about the residuals inside the domain, because you know that it just has to satisfy a PDE constraint. And so this makes you, if trained properly, randomly sampling at new points at each iteration, this kind of gets rid of the notion of overfitting, which is a problem that we've seen in some experiments these KST architectures have, right? So since we have basically infinite data, we don't really care too much about overfitting, and so this begs another this has another advantage. Another thing is that since we're going to have to take derivatives of the network with respect to its inputs, the derivative information is very important. And if you use an MLP, for example, with ReLU, no matter how you do it, the first derivative is always going to be piecewise constant, and the second derivative is always going to be 0, right? There's other things that you can do that is not always like that, but having the exact representation kind of maybe gives you a little more hope that you're also going to preserve some of these derivative information. And last but not least, honestly, a little bit of hype, you know, like this paper came out, there's a lot of interest and a lot of people excited about this, and just seeing like, oh my God, I have this idea. Can I try it out? Can I be like the first person to put it out? And I think that does motivate a lot of work in the past few months. I'm not gonna lie, probably like also like a little bit of my own paper, you know? But one thing that I will say about ActNet with regard to these things and its applicability to pins. Oh yeah, so before, let me talk about that. And speaking of hype, I guess, it's not all just pure happiness. There have been some controversies or just like criticism on like experiments regarding cons. So there's just like two of the papers that talk more about it. The paper on the left specifically focused on scientific computing for like pins and some operator learning, and on the right is a little bit more broad. And these two papers had some trouble reproducing some of the things from the Khan paper, or said that maybe some of the stronger claims didn't really hold when you look into other data sets. So that could be like potential thorn in the rose, and is it worth pursuing this altogether? And I will make the argument, at least for ActNet, for pins, that there is a very attractive property, which is that the derivative of an ActNet of an ActLayer is another ActLayer. So there's a little bit hand wavy, but gives you an idea. So if you look at if you take the partial derivative with respect to an input of an ActLayer, and you do a little bit of math, you get that the Jacobian is going to have this structure over here, okay, where lambda is again that learnable parameter, and this phi prime is the first order derivatives. It's kind of like another basis expansion, but instead of using the original functions, now I use the derivatives of the basis functions. So if we pick the right basis functions, which we use, again, sinusoidal basis functions instead of polynomials, polynomial derivatives eventually vanish to zero. Sinusoidal ones from the basis we were using do not vanish to zero. So this kind of gives you a little bit better hope that it's going to be able to approximate these higher order derivatives for your system. Now it's a little bit hand wavy because again, now we're talking that this is a Jacobian, whereas the output of a neural net of the ActLayer is a vector as opposed to a matrix. But you get the idea. If you keep on taking these derivatives, it's not going to automatically vanish to zero. You're still going to preserve some of the derivative information. All right. So last but not least, let's talk about some experiments and put the applied in applied math. So I did try to do my best to run fair experiments across different methods. I split my experiments in two types. I ran some ablation experiments where I was comparing ActNet with other types of neural network architecture, particularly CUNs. Also just like a plain MLP, a base MLP, and a siren network. If you're not familiar with siren, a siren is a multi-layer perceptron, but with the activations used as sign, and it also has a special initialization procedure. So you basically have over here kind of like two representatives for multi-layer perceptron, two representatives for Kolmogorov Superposition Theorem things, right? And I ran, so for these ablation experiments, I ran across several different, for each of these architectures, I chose several parameter sizes. So several different network sizes. For each network size, I looked at 12 different hyperparameter combinations. So I kind of ran a little sweep. For each hyperparameter combination, I ran 3 different initializations and took the median value. And then based on that median value, I only considered the best hyperparameter choice. So this is to give the best shot at each of these networks, each of these different types of architectures. And so for the ablation experiments alone, I had to train independently a little over 7,000 networks. So it's a lot. And then I see like, wow, you burned a small forest for that. And I will say, those are all like relatively small scale experiments. I did actually do the math because you can see the energy utilization of each GPU to run these like over 7,000 experiments. I think it took the energy consumption roughly of like a fridge running for about 2 weeks. So not nothing. It's the fridges do use electricity, but not that bad. I'm not training a large language model from scratch. So I try to be very thorough with a lot of small scale experiments. And for the second part of the experiments that you see over here, I looked at much more challenging problems, and instead of running a lot of like different sweeps, I said, okay, I'm only gonna run ActNet, and instead of comparing to the other architectures, I'm gonna compare to other state-of-the-art methods. I'm not gonna run any other code, but I'm gonna see what other papers report as their best performance, and I'm gonna see if I can beat that on some challenging problems. So let's first talk about some of these ablation experiments first. So first off, I tried the Poisson PDE, which basically just tries to talk at, you want the Laplacian of your function to be equal to this forcing term f over here, and I assumed zero boundary condition. And I also looked at different values for this f over here. And I tried to look, talking about the spectral bias that I was talking about, what happens if we make this ground truth more and more oscillatory. So you can see you start with low frequency over here, and as you go further, you get higher and higher frequency content. So these are 6 different PDEs. They're solved independently. They're just like, I'm solving the PDE, Poisson PDE, different times using different things, and I'm seeing how does it perform when we are looking at low frequency content or high frequency content. And the result is overwhelmingly that ActNet outperforms a lot of all the other ones for almost all cases. You can see over here, so on this first block is parameters with 10, like networks with 10,000 parameters, then 20,000 parameters, 40,000 parameters, and 80,000 parameters. And you can see each representative, and on the y-axis over here, you have the frequency. And you can see the only cases where other networks outperform ActNet at the same parameter level is at the very like low frequency. Sometimes, for example, is 1.2 e to the -5. This is also 1.2 e to the -5, but just like a little bit. So probably at this point also, we're talking about an error of 0.01, no, 0.001%. This is relative L2 error. So this is like very precise and up to machine precision at that point. So some differences are inevitable. But particularly as you go to the more challenging cases over here, you can see that we can get ActNet to perform with 32% relative L2 error, not great, but the other ones are on the order of like 100% relative L2 error. They're just like way off. And you can see some of this, for example, over here. For the highest frequency content, you can see the ActNet absolute error over here in the ActNet prediction compared to Siren, which was the other best performing one. And you can see that they do learn something a little similar this time. For the largest value of Siren does put like a good fight, but there's still like a lot more error, right? I also look at the Helmholtz PDE, which is very similar to the Poisson PDE, but you have this extra term over here. That now you have to mix information of the Laplacian with the values of the function itself. And I did the same thing so that we get different solutions, and we do know true analytical solutions for both the PDE and the Helmholtz case in this case. And you can see very similar behavior. Overall, ActNet does outperform the other architectures across a wide range of frequencies and parameter sizes, with a few exceptions, which are honestly expected. You're never going to have something that beats everything in every possible scenario. So you can see over here some, this is for like the frequency 16 in this case, and you can see that ActNet can do like a really, really good job. You can barely see any error over here. Siren does a little bit better job, but you can see like a little bit of color over here, and Con does very badly. And I'll say in general, that is a common trend in all my experiments. Usually the worst performing architecture tended to be Cons. Not say that their architecture is bad or anything like that. It could also be issues of like the way that I'm implementing it. But I will say, even though my implementation of Con does worse than the other ones, it still does perform generally much better than what the people report in the original Con paper. But yeah, the final experiment PDE that I consider for these ablations is the Allen-Kohn equation. In this case, we don't have an analytical solution. We have to use a reference solution from like classical numerical methods. And in this case, you actually see that ActNet performs best for small network sizes, but for large network sizes, we actually see Siren working best, which I thought was really interesting. Another thing that is interesting is, despite Siren working better for larger network sizes, the residual loss, which is what we train on, is always smaller for ActNet, which makes me think that maybe there's also some like floating point precision here, because once again, all these results are generally very accurate. And there is a limit to what you can do with single point precision, which is how I ran all the experiments over here. So there is a possibility that maybe for larger network sizes, there's a little bit more floating point arithmetic mismatch from our ActNet, maybe because of my own implementation. But overall, they all perform pretty well. You can see they all get relative L2 errors on the order of like e to the negative 5, like 10 to the negative 5, right? So very, very precise overall. Now, very quickly, I'm going to talk about the two comparison against what we call state of the art. We look at the advection equation, which you can see over here, with a very high transport velocity of 80. And in this case, these are results from like other two papers, youth training on pins. And in this case, I didn't run a lot of the other ones. I just like focused on ActNet, and I see if I could beat. And indeed, I could actually beat these other state-of-the-art results on this like challenging problem. You can see these have like very high oscillatory behavior. The other ones, the best they can do is like something in the order of like 5 or 6 or 7 to the negative 4, and we can drive just below around like 9 to the 10 to the negative 5. So that's an improvement that shows that it can compete not just with other naive things, but it is competitive against state-of-the-art methods. And finally, I want to talk about, I also tried on the Kuramoto-Sivashinsky equation, which is a very hard equation to approximate using numerical methods. It is a chaotic fourth order PDE. And you can see over here, time is on the x-axis. And as you progress, all the errors concentrate on the right. And as you progress, since it's a chaotic system, every small little difference does lead to an impact later on. And this actually we saw like a large improvement where like PirateNets, which is a state-of-the-art method, gets around 21% relative L2 error. JackSpy gets about 16%. We managed to drive that down to 8, so about half, which is pretty good. And this is a really hard problem to solve because you actually have to like solve each window independently at a time. And if you look only the first time window, you can see we get some PirateNet gets slightly lower. It gets 1.23. We get 1.34, but very precise things. And at least in this experiment, ActNet did have more stable rollouts if you look at the final solution. And yeah, just as a very quick conclusion summary, I do think that these KST-based approaches have potential for deep learning. I don't know what all the possibilities are. I don't think it's necessarily going to revolutionize all of deep learning, but I do think there's interesting use case applications for it. I also talked about ActNet, which is a novel neural network architecture that has universal approximation, has a stable initialization that keeps the activations stable throughout the network. It also has good derivative properties, and our experiments do show that ActNet performs very well, particularly for physics-informed applications. And as I mentioned before, the main limitation of these KST approaches is that they still lag behind traditional MLPs when it comes to computational speed, but there are also things that can potentially be done to the implementation and tweaks to simplify some of the math that can maybe bridge that gap and make it a little closer. And that is all. Thank you so much for having me. I'm posting the QR code for the paper if anyone wants to take a look. Once again, if you're going to be in ICLR, come chat with me. And as a last plug, this morning I got an email saying that they chose me to give this like Penn grad talks thing. It's like a competition of like TED style 8-minute talks between grad students. So if you can see me speak about that in a couple of weeks, I'm going to talk about some like uncertainty quantification stuff, how to know what you don't know. I thought that was catchy. But anyway, thanks so much for having me, and I'm happy to answer any questions. Sorry for running a little bit over.